Alright, so back again with another proof video. And this time we're going to prove that the square root of 3 is irrational. Alright, so the way I want to do this is, I want to start by assuming the opposite. So we're going to assume that the square root of 3 is actually rational, and then we'll argue to a contradiction. So, assume that the square root of 3 is rational by contradiction. Okay, so if the square root of 3 is rational, then that means we can write this number as a fraction. So then the square root of 3 is equal to p over q, where p and q are whole numbers, so we'll just say they belong to the set of all integers. And we can also say that the greatest common divisor of p and q is 1. And when we say that, that just means that this fraction is already in the simplest form, right? So it can't be reduced down anymore. But we also have to assume that q cannot equal 0. And that's because if q was 0, well, then we'd be dividing by 0. And we can't have that. So q can't be 0, but p, of course, can be 0. That would be fine. Okay. So then by the fundamental theorem of arithmetic, which states that we can actually take these whole numbers and we can write them as strings of prime numbers, we can say that p is equal to p1 to the alpha 1 power, p2 to the alpha 2 power, all the way to p of n to the alpha n power. And all these p1s, p2s, p3s, all those are just prime numbers, right? And the alpha 1, the alpha 2, all the way up to alpha n, these are the exponents. So that tells you how many times these primes are going to show up. Okay? So we can write p as the product of distinct prime numbers. But if we can do that for p, we can also do that for q, right? So I'm going to write q as q1 to the beta 1 power, q2 to the beta 2 power, all the way to q of n to the beta n power. So we can get all these exponents, the alpha I and the beta j, these are all at least 0, right? And we can say that the pi and the qj, those are all just distinct prime numbers, like I've said before. So these are all distinct primes. Okay, so then here's where the algebra comes in. We're going to take our original statement, the square root of 3 equals p over q. We can take this statement and we can square both sides. So if I was to square both sides, I would have to square this side and this side, and I would get 3 is equal to p squared over q squared, right? And then we can take that and we can multiply both sides by q squared, so that p squared will be on the right side by itself. So I get p squared is equal to 3 times q squared. Okay? So now I've got p squared equals 3 times q squared, and I already said that p was equal to this long expression, right? And q is equal to this long expression, and we're going to substitute those in for p and q. So I'm going to get p squared. We know that p is going to be p1 to the alpha 1, p2 to the alpha 2, all the way to pn alpha n, and I'm going to square it because I have a square right here. We're going to square that. we're going to have it equal to 3 times q squared. So I'm going to have a 3, and then on the inside I'm going to put q, which is q1 to the beta 1 power, q2 to the beta 2 power, all the way to qn to the beta n power. So this whole thing is going to be squared as well, because this q is squared. Okay. So now we're going to use an exponent rule, where we take the exponents and we multiply them all by 2. So I'm going to get p1 to the 2 alpha 1 times p2 to the 2 alpha 2 all the way to pn to the 2 alpha n. And then I'll do the same on this side, but the 3 is going to be out in front. So I'm going to have 3 times q1 to the 2 beta 1 times q2 to the 2 beta 2 all the way to qn to the 2 times beta n. Okay? Now, we're going to assume that the first prime is going to be 3. And that's going to help us in our proof. And I'm going to assume that the first prime number is 3. Now, of course, 2 is also a prime number, and it's the first prime number, but it's going to be some other prime, not the first prime. Okay? So then, what can we say about the number of 3's that show up? Well, if you look on the left side, how many 3's are going to show up here? Well, if alpha 1 was 0, then I wouldn't have any 3's to speak of. But if alpha 1 was 1, I would have p1 squared, which means I would have 2 of the 3's, right? And if alpha 1 was 2, then I would have 4 of the 3's. And that pattern is going to continue to repeat. So then we can say the number of 3's on the left side is, it could be 0, it could be 2, it could be 4, it could be 6, and so on, just increasing by 2 each time. And what can we say about the number of 3's on the right side? Well, this coefficient is going to come into play, right? There's at least going to be 1 3 on this side, right? So even if I have 0 3's right here, I still have 1 3 right here, so I'm still going to have 1 3, right? So I can say the number of 3's on the right side is what? The number of 3's on the right side is, it could be 1, but then if beta 1 was equal to 1, then I would have 2 3's, plus this one right here would make 3 3's, so I would have 3, and then the pattern would continue, right? Adding 2 each time. So I could have 1, 3, 5, 7, and so on, right? So the number of 3's on the left side is always going to be different from the number of 3's on the right side. Thus, these two sides cannot be equal, right? So we started off by assuming that p squared is equal to 3q squared, but that is not true. These two sides cannot be equal because there's a mismatch, right, on the number of 3's that show up. So this is a contradiction. Therefore, our initial statement that square root of 3 is rational is false. Square root of 3 is irrational. So actually, I cannot write this number as a fraction, like I tried to up here, right? Just can't do it. So some numbers you can't write as fractions, and those are called irrational. Okay? So I'll zoom out so you guys can see the full proof. There we go. Alright, so square root of 3 is irrational, and I'll be doing a square root of 5 proof, and then have enough information to make an inference that the square root of any prime is irrational. So I hope that helps.